All right, can everybody see my screen and see question 24 that deals with a polymer? All right, perfect. Awesome. So question 24 asks us, what monomers are needed to produce this polymer? Well, this is a condensation polymer, isn't it? Right? This is a condensation polymer, and it's a polyester. How do we know that? Because we have an ester bond right here. Well, what do you make an ester from? You make an ester from a carboxylic acid and an alcohol. And you can see the repeating unit here, and that the ester bond is right here, okay? So that tells us that from this part over here, this is where we would get our diacid from. Which would be succinic acid. So if we look over here in the answers, the only one that has succinic acid is this one here. And then our diol would come from this portion here, and that would come from ethylene glycol, which is here as well. And so if you were to take, succinic acid and ethylene glycol and put them together and drive off water, you would end up with that polyester. Okay, and if you need to review polymers, that's chapter 27 from our textbook. Okay, let's do another one here. Question 25, one of the most famous reactions in organic chemistry. It says, what's the product formed from this reaction? We're starting with a methyl ketone. So it's very important that you start with a methyl ketone. And in the first step, you treat it with chlorine and sodium hydroxide, and then you treat that with water and acid, okay, to do some kind of hydrolysis. Now, hopefully you remember that this is called the haloform reaction. So this is the, I'll write it down here, this is the haloform reaction. And if you do it with chlorine, it's called the chloroform reaction, and you have the bromoform reaction, and you have the iodoform reaction. Anyhow, so what happens is, remember, you've got, an acidic proton here, so the sodium hydroxide is going to abstract. It's going to abstract that proton, and you're going to end up with this enolate. Okay, you're going to end up with this enolate here, right? And then that's going to react with chlorine, right? That's going to act as a nucleophile and do an SN2 reaction. And then you do that a couple more times, and you end up with the trichloromethyl ketone. So instead of having CH3, you have CCl3. And then in the last step, you're going to hydrolyze that with acid, right? Because this has now been converted into a good leaving group because of the electron withdrawing effect of those three chlorines. And so you end up losing chloroform and converting the trichloromethyl ketone into a carboxylic acid. And so in this case, you would end up with benzoic acid, and of course you end up with CHCl3, which is chloroform, as a byproduct as well. So that's the haloform reaction. Make sure you know the haloform reaction, very important reaction in organic chemistry. One of the classics. Okay, let's move on from there. Look at question number 26. So this one deals with electrophilic aromatic substitution. Which position will be attacked most rapidly by a nitronium ion when the compound undergoes nitration with nitric acid and sulfuric acid? Well, remember that the nitronium ion, which we studied in detail, if you take chemistry 3112, we would have looked at it in that class as well. It's a powerful electrophile, right? Very powerful electrophile. And so then the question becomes, okay, well, where is it going to go? Is it going to, will the nucleophilic attack, occur on carbon A, B, C, or D, right? Could this happen, for example? Is this likely to happen, right, in the nitration process, right? You generate the sigma complex, and then you deprotonate to restore aromaticity. Well, the answer is no, it's not going to occur at A. And the reason why is because when we have a ketone here, we have this electron withdrawing substituent like that, right? And that is a deactivating group. If you remember, again, electrophilic aromatic substitution, a ketone is a deactivating group, so deactivator, and so it's not going to react on that ring, whereas here we have a methyl group. Now, a methyl group is a weak activator, but it's still an activator based on hyperconjugation. So then the question becomes, is it going to attack, or will the nucleophilic attack via carbon D or carbon C? So we have to examine those two positions, right? Carbon D is ortho with respect to the methyl group, and carbon C is meta with respect to that. Now, hopefully you remember that when you have an activating group, like a methyl, even though it's a weak activator, that the nucleophilic attack or the electrophilic aromatic substitution will occur at the ortho or para position. Now, the para position is blocked, and so the substitution will occur at D. Now, I'm not going to go and draw the whole sigma complex, but if you draw the curved arrows, right, for this step here, okay, you're going to end up with a positive charge right here, right? You're going to end up with that carbocation, and that carbocation is going to be stabilized by hyperconjugation from the methyl group. So if you need to review that, that would be chapter 18, okay? Aromatic substitution, if you need to review, you know, what's an activator, what's a deactivator, and all that kind of stuff that we looked at in that chapter. Okay, question 27 is another polymers question. So it says the copolymerization of vinyl chloride and vinylidene chloride, and the structures are shown here. You don't have to memorize the structures of vinyl chloride or vinylidene chloride. By free radical catalysis produces a polymer used in food wrap. You can probably guess where we're going with this, right? You remember that we talked about saran, which is the name of a polymer, and then it's marketed as saran wrap or plastic wrap if it's generic. Which structural unit would appear in this polymer? Well, we're going to connect these two monomers, right? Vinyl chloride and vinylidene chloride. And remember what I told you is that you're going to remove the pi bonds, right? And then you're just going to connect these by sigma bonds, okay? Like that. Now, the first one, we have vinylidene chloride here, but the vinyl chloride is reversed, so that's not right. Here we have, in B, we have the vinyl chloride portion here, and then we have the vinylidene chloride portion here, so that's correct. The next one, you have the vinyl chloride reversed, so that's not right. And in the last one, well, that's just plain wrong. I'm not even sure what's going on here. Okay, so the answer would be B. And saran is a polymer that we looked at. It's a very specific example that was shown in our textbook in question 27 and chapter 27, right? Anyhow, number 28 just deals with some oxidation conditions. Which compound can most easily be oxidized by potassium dichromate and sulfuric acid? Okay, so this is just a way of making chromium-6, which is a strong oxidizing agent. Well, the first one, A, that's a carboxylic acid, so that's not going to be further oxidized. The next one is tert-butyl alcohol. You can't oxidize a tertiary alcohol, can you? If you try to take a tertiary alcohol, let's just draw, you know, a tertiary alcohol, and you try to oxidize that, you're going to get no reaction. Why? Because the carbonyl-carbon does not have a hydrogen directly attached to it. Also, a ketone is not going to be oxidized, whereas an aldehyde, right? This is an aldehyde, and you have to know the condensed structure of an aldehyde, right? If you had this, okay, if you had C2OH, right, that's an alcohol. But when you have CHO, that's the condensed structure of an aldehyde. So if we try to oxidize this, it can be oxidized to a carboxylic acid. So you'd get cyclohexane carboxylic acid like that. So the answer is D. You can oxidize an aldehyde. All right. Let's take a look here. What's the expected product of this reaction? This is SNAR chemistry. All right. So if you've forgotten your SNAR, this is in the aromatic substitution reactions chapter as well. So this would be chapter 18 and towards the end of that chapter. Right, and we looked at the Meisenheimer complex. So if you need to review what a Meisenheimer complex is, make sure you review that. Okay, and you remember that in order for a nucleophilic aromatic substitution reaction to occur, you've got to have a strong nucleophile. Well, we've got that, right? We've got methoxide, so that's good. You've got to have a good leaving group. We've got 2 chlorines. Those are the chloride is the conjugate base of HCl, so that's a good leaving group. And you've also got to have a strong electron withdrawing group. And what are the requirements? It has to be either ortho or para to the leaving group. And so the nucleophilic attack is not going to occur on that, is not going to occur on this carbon, is what I should say, right? It's only going to occur on the carbon that has the chlorine position ortho or para to the strong electron withdrawing group. So we're going to get our SNAR chemistry like that. Now that's an abridged version of the mechanism, right? Technically, you should draw the Meisenheimer complex, but when you do that, you should be able to show that the negative charge, right, from the methoxide is going to be delocalized down on the nitro here and on this one as well. And so if you look at this one here, the methoxy's in the wrong place. It's in the wrong place here. It's definitely not going to be meta, so we'll put not meta to electron withdrawing groups. So that's a big no-no. And C would be the correct answer, and I don't even know what's going on in D. That's nowhere near correct. So the answer is C. So nucleophilic aromatic substitution, Meisenheimer complex, make sure you review that. I finished making up the exam over the weekend. There's definitely a question about that. Let's see. What is the main product of alkaline permanganate oxidation after neutralization? So if you take this, so this is propylbenzene. You treat it with potassium permanganate and base, and then you do an acidic workup. This is a benzylic oxidation, right? So this is benzylic oxidation. And you remember that the way the book phrases it is he says you excise the remainder of, of the compound. Now, what does that mean, right? Here's your benzylic hydrogens right here. So you're going to oxidize that carbon that I have circled in blue, and all the rest, all of this part here, that's just going to go away. Okay, and you're like, where does it go? Well, you can't destroy matter, but it's going to end up, some kind of byproduct in the reaction that you can extract out or something. Okay, so since you're only oxidizing at the benzylic position, you're going to end up fully oxidizing that carbon. What's the fully oxidized form? It's going to be benzoic acid, carboxylic acid. So that's benzylic oxidation. Again, that's a specific reaction that we studied over the course of the semester. Well, let's take a look at question 31, which deals with some infrared spectroscopy. We have a beautiful spectrum here, and it says, which structure is most consistent with this IR spectrum? Oh boy. Well, the first thing I notice on this is that you have two absorbances right around here. And those absorbances are around the 3550 to 3250 region. And when we have two absorbances like this is because we have a primary amine. So primary amine, okay, because you're going to have symmetrical stretching, right, and you're going to have asymmetrical stretching. And I covered that with you in class, okay? So we have a primary amine here, here, and here. So that means we can eliminate C because that's a secondary amine. What else do I see here? Something else that really sticks out at me is that we have an aromatic ring, don't we, right? There's some confusion, I think, sometimes about aromatic stretching, right? Carbon-carbon sp2 hybridized aromatic stretching. Those peaks are manifested as usually 2 to 3 peaks in the 1475 to 1450 to 1600 region. Okay, so these absorbances that I have circled in blue, these are sp2 hybridized carbon-carbon stretching, and these are aromatic. So the compound is aromatic, and we can eliminate this compound. Now here I have aniline, and here I have paramethyl-aniline. Could anybody give me a clue as to which one of these it's going to be and how you figured it out? Does anybody have an idea? Well, I would say the key is in this absorbance right here, right? The ubiquitous or semi-ubiquitous sp3 hybridized carbon-hydrogen stretching, right? We see that in most compounds in organic, not all, but we see it in a lot of them, right? Because there's usually, a lot, or most organic compounds have some kind of sp3 hybridized carbon-hydrogen stretching, right? We don't have any sp3 hybridized carbon-hydrogen bonds here, right? It's only has only sp2. Okay, whereas this compound does have sp3 hybridized carbon hydrogen stretching, and so the answer would be paramethyl aniline. Okay, let's move on to the next question. Question 32 deals with carbon NMR. Got a compound here, so we have, this is called a carbamate. This is one of those functional groups that we don't see a lot of in this class, right? Looks like you have an amide on one side and then an ester on the other, so that's called a carbamate or a carbamate. It says the chemical shifts for the carbon-13 spectrum for this compound are 15.8, 40.1, 51.8, and 170.2 parts per million. Which is the correct set of chemical shifts for the carbon atoms? Well, the first thing you should know is that the one that has the carbonyl, okay, that's going to be the most deshielded, and so that's going to have the highest chemical shift. So that's going to be 100, what is it, 170.2. So if we look at carbon atom number 2, we can cross off these two. It must be 170.2. The easiest way, I would say, to solve this problem after that would be to look at the least deshielded carbon, right? Carbon number 1 is attached to an oxygen, so that's got some deshielding. And carbon number 3 is attached to a nitrogen, but carbon 4 is, far enough away from a nitrogen that it's going to be the least deshielded, and it should have the lowest chemical shift. And so the lowest of the low is 15.8. So this is 15.8 parts per million. And so that would mean that it is going to be D, like that. And if you think about, carbons 1 and carbons 3, well, you could rationalize the carbon 1 is going to be more deshielded because it's attached to an oxygen, which is more electronegative than a nitrogen, like that. Okay, let's move on from there. We solved that one by process of elimination more than anything. Let's do number 33. I think I asked you this, or I had this same question in a review set that we did back in May. If you took this class with me in the spring semester, it's one of my favorite questions, I guess. But it's asking us, which of these compounds will show 2 triplets among other signals in their NMR spectrum. So let's start by looking at number 1. And if we look at number 1, you see you have a methylene here, right? You have a CH2. Well, what kind of splitting is that going to give you? It's coupled next to these 2 protons. 2 plus 1 is 3, so that's a triplet. Okay, so that looks pretty reasonable. If you look at this methylene here, it's coupled by 2 sets of protons that are not equivalent, right? We have 1 proton here and we have 2 protons here. So that's going to give you a multiplet. Now it's going to give you a doublet of triplets or a triplet of doublets. Either way is fine. So we can say here doublet of triplets, or if you want to write triplet of doublets, that's fine too. But either way, it's not a triplet, right? Whereas this hydrogen right here, that is coupled next to 2 equivalent hydrogens. So 2 plus 1 is 3. So that gives you a triplet. That means that we can erase D because we know that 1 has 2 triplets in it. Okay, I'm going to use a different color to analyze number 2. Now, number 2 has a plane of symmetry in it, doesn't it? All right, it has a plane of symmetry in it. If you look at these protons and these protons here, right, those are chemically equivalent, aren't they? Right, because of the plane of symmetry down the molecule, and they're both coupled next to these 2 protons in the middle like that. So since these 2 sets of these 2 methylenes are chemically equivalent, they will both produce a triplet, but it's the same triplet, right? You're not going to see 2 different triplets, and it's asking us, 2 triplets. That's not 2 triplets. It's going to show you 1 triplet. How would you know that there's 4 protons? By integration, right? Now, if you look at the methylene that's in the middle here, it's coupled next to a total of 4 protons, and so it's going to give you a quintet. Okay, so we can eliminate any answer that's got number 2 in it because it doesn't give you 2 distinct triplets. It gives you a triplet and a quintet. All right, let's look at the last one and see if there's 2 triplets in here. Well, if I analyze this methine here, it's coupled next to these 2 protons, so that's definitely going to give me a triplet. If I look at this methylene here, it's going to give me a triplet because it's coupled next to, try to use a different color here. It's coupled next to 1, 2 protons. So it is going to give me a triplet. I was supposed to use green, wasn't I? It's going to give me a triplet. And then again, there's a plane of symmetry in this molecule, and this hydrogen is going to give you the same triplet as this one, but we have two distinct triplets, don't we? We have the one that I have circled in green and the one that I'm circling in yellow. And so the answer is that both compounds 1 and compound 3, they both produce two different distinct triplets. And so that's the answer. It's compounds 1 and 3. And this is a classic, kind of ACS question where they love to ask more than one thing in the same question. All right, let's move on and take a look at question number 34. This is something I feel like we did, Avogadro's number of times towards the end of Chemistry 3101, right? We looked at terminal alkynes, I don't know how many times, because it was one of the few ways that we learned to make carbon-carbon bonds in Organic Chemistry 1. So if you take propine, so this is propine, and we treat that with sodium amide, right? What's the amide going to do, right? NH2 minus. It's going to do a deprotonation, right? That's something that we did, Avogadro's number of times last semester. So you make the acetylide ion like that. Then you're treating it with methyl bromide, which is a very powerful electrophile. So you're going to get an SN2 reaction. So you end up with 2-butene, compound that everybody knows. So you end up with 2-butene. And then you just do a hydration, right? Remember, when you hydrate an alkene, you just need water and acid. But with an alkyne, you need something to help you along, and that something is mercuric sulfate. We went over that very briefly, just kind of touched on it. And our book goes into maybe a tiny bit of detail about what the mercury is used for, but you need that mercury to help that reaction to work. Then you end up with this compound, right? You end up doing a hydration. Now there's a symmetry in this molecule. So Markovnikov or anti-Markovnikov is neither here nor there. Let's just put the hydroxyl here, okay? And then we end up with CH3. Now, what kind of compound is that? That's an enol. And we know that enols undergo tautomerization, don't they? And this enol would tautomerize to give you butanone. So this is butanone, okay? Remember, it's not 2-butanone, it's just plain old butanone. If you put a 2 in front of there, it's redundant because there's only one position that the carbonyl can be in a 4-carbon straight chain ketone, like that. All right, there we go. Give me a thumbs up if you follow me on that one. The enol that tautomerizes to give you a ketone. Excuse me. All right, I got one person giving me a thumbs up. Oh, 2. Okay, times are hard. Okay, here we go. Let's look at another problem. Let's see here. This one deals with diazotization, right? We looked at diazonium ions, and it says here, which sequence of reagents will accomplish this transformation? So we want to take paramethyl aniline, and we want to convert it into 3,5-dibromotoluene. Okay, so how would we do that? Well, if we look at the first one, if we were to do A, the first step is just diazotization, right? That's converting that, you'd be basically converting that compound to the diazonium salt, right? When you treat it with sodium nitrite and HCl, you'd end up with this, N2 plus, right, Cl minus, okay? I got the diazonium salt, and then when you treat that with cuprous bromide, copper 1 bromide, right, then you would just replace the diazonium with the bromine. So that doesn't help you at all. That doesn't get you anywhere where you need to go. The next one is you're taking the diazonium salt and you're diazotizing it. Let me just erase this and we'll kind of look at them. And then you treat it with hypophosphorus acid. So that's a real chestnut. We only looked at that once, right? Hypophosphorus acid. Okay. So after you've done that, you'd basically be eliminating this, you'd be eliminating the diazonium salt. So you'd be converting this to a hydrogen. And then it says you're going to do a bromination. Well, methyl we looked at already today is an orthopara director. So that means you'd get bromination here and here. So that doesn't help you either, right? That gets you nowhere you need to go. So let's eliminate that one. The next one is just bromination followed by lithium aluminum hydride. Well, if I was to try to brominate paramethyl aniline, right? The aniline is a strong activator. It's a strong activator. And this is a, something that we look at. If you were to brominate, just treat this with bromine, you actually do end up with the bromines in the right position. Okay, you'd end up with a bromine here and a bromine here. But once you treat that with lithium aluminum hydride, that's not going to react. There's nothing in there for it to react with. But if you look at the last one, okay, the first step is bromination. I have that completed. The next step is going to be diazotization, right? You're going to convert the aniline into the diazonium salt, like that. And then in the last step, you treat it with hypophosphorous acid, and you're going to blow off that diazonium salt, and you're going to convert that to a hydrogen, and that is the correct compound. And so the answer is D. This is a real hardcore, synthesis problem. Just good old synthesis, and also knowing your electrophilic aromatic substitution. And this, I believe, we looked at this also in the amines chapter. So, you can see there's a lot of electrophilic aromatic substitution on the exam. Very important chemistry. Okay, I remember my first interview that I did in industry. My supervisor before I went out there, he released me and he said, just make sure you're tight on your electrophilic aromatic substitution because it comes up a lot in organic, especially in synthesis. Okay, last question in the quiz is: an unknown compound was found to be unreactive towards chromic acid and gave this infrared spectrum. What is a likely structure for this compound? Okay, well, let's take a looky here. Something I noticed right away with, I'm sure you all noticed this. You have the oxygen hydrogen stretch of an alcohol. Okay, so we can eliminate this ether, but the other three, those are all alcohols, aren't they? Right? Okay. Something else I noticed is that all of them every single choice is aromatic, isn't it? All right, and you can see, you've got the aromatic stretching. That's these right here, right? We have two peaks in the 14, 50 to 1600 region. Also, everybody, my students seem to be obsessed with overtones. Overtones, those are in the region of 1667 to 2000 reciprocal centimeters. Okay. What else? Anyhow, that's enough for now, because there's another clue that they give you in here, isn't there? Right? How would you differentiate between these alcohols? It says unreactive towards chromic acid, right? Unreactive towards chromic acid. Well, if it's an alcohol, right, and it can't react with chromic acid, that tells you that it must be a tertiary alcohol, right? So kind of a double whammy here, right? First, you're asked to interpret an IR, and you eliminate the ether, and then it tells you that it's unreactive with chromic acid. Well, benzyl alcohol is a primary alcohol. This is a secondary alcohol, but right here we have a tertiary alcohol. This is a question I would expect everybody to get, when I'm going through the grades. Okay, so let me just make a note here. All right, there we go, and that covers the entire quiz, or the Chemistry 3111 final exam review.